All right, hey everybody. Today we're talking about a new unit, which is on thermodynamics, as you can see. And what we're going to do with this unit is that a lot of the discussion of fluid mechanics so far has focused on forces and pressure um, and maybe momentum a little bit. We haven't really talked about energy so much, and so that's what thermodynamics is going to do. It's going to introduce the idea of energy into our discussion of fluid mechanics. Um, and so that's the name of this topic of how energy relates to fluid mechanics is thermodynamics. And there's a couple of laws of thermodynamics. I'm going to give you kind of a lightning overview of what those laws are. And then later we'll talk about the different thermodynamic processes that happen. And there's only a couple of them. And so I'm going to give you an overview of those. So the first thing you need to know about thermodynamics is that there is this property called temperature. And every object has some kind of a temperature. And if you put another block next to this block, which has temperature T1, and the other block has temperature T2, you stick them next to each other, and allow them to exchange heat, eventually they will come to some temperature that is in between those two temperatures. So again, exactly how that temperature is determined is not so important right now, but if there's two things that have two temperatures, they tend to equilibrate those temperatures. The next thing that you need to know is that the relationship between energy and temperature is not always so simple, which, for example, if you have ice and you're adding heat to ice, that doesn't always increase the temperature. And if you know a little bit about ice, you know that what's happening is that there's a phase change. But for our purposes, what's interesting is that you're adding energy to the ice, so there's a little flame underneath this thing, and all you're doing is converting it from the solid phase to the liquid phase. It is not actually heating up. It might still be at 0 degrees centigrade. So again, the relationship between the energy of the object and its temperature can be surprisingly complicated sometimes. But if nothing is changing phase, then the energy and the temperature are proportional to each other. So for example, to increase a sample by some number of degrees Kelvin, it takes a certain amount of energy to do that, and there's a constant here multiplied by that temperature change. It's called the heat capacity. And so there's a whole class of problems of if I want to increase the temperature by 10 degrees, multiply this times heat capacity, figure out how much energy from this campfire that it took to do it, or if I want to figure out if I dump a certain amount of energy onto some sample, I can divide that by the heat capacity to figure out how many degrees it's going to increase the sample. So we'll get into that a little bit later. The fourth thing to know is that this idea of heat and temperature is related to motion. So we've talked about how the molecules in this room are zipping around at 340 something meters per second. And if you heat up the air in this room, it'll go faster than that. If you cool down the air in this room, it'll go slower than that. So that's true of all gases, helium, whatever carbon dioxide in a soda bottle, whatever you got. But it's also true of solids. So solids, we don't necessarily think of them moving, but solids do vibrate. And so this video here, which I did not make, but it's pretty cool, this video shows basically what's happening inside of a solid is that, specifically a solid with non-zero temperature. And so it's kind of wiggling around like so. And if you heat up the solid, even though the solid still stays there intact, you're going to make these things wiggle more and more. And so any kind of discussion of heat and temperature is also a discussion of some sort of motion, whether it's vibration or whether it's molecules or atoms zipping around. A fifth thing to know is how to convert from Celsius to Kelvin, things like that. I don't really care that much if you can convert from Fahrenheit to Celsius. But I do care very much that you appreciate that if you have temperature in Celsius to get Kelvin, you add 273 to it. So room temperature, I forget, is maybe like 25 degrees Celsius. So 25 degrees plus 273, that gives you 298, almost 300 Kelvin. So a lot of times we just say, you know what, room temperature is 300 Kelvin, and that's good enough. But very often on tests, I'll give you Celsius, and the thing that you'll need to do the temperature for the calculation is Kelvin. So in all of the equations that we talked about last time with the ideal gas law, those temperatures were all in Kelvin, not Celsius. But I will often give you Celsius just to see if I can trip you up a little bit. So anyway, so be on your guard about that. Probably you already knew this, but anyway, 1 year with the OSU Marion trivia contest, this is the only question I got right. I'm not terribly good at trivia, but I got that one. All right. Now there's a couple of thermodynamic processes that I'm going to talk about in the next slide, and a lot of them have the phrase iso in it. Iso means the same. So for example, a triangle that has two equal length sides, like this, like that. So not so much a triangle that's like, I don't know, that has three different sides or three different lengths. But if they have two equal length sides, that's called an isosceles triangle, which comes from iso, which means the same. So these are the thermodynamic processes. So there's constant volume processes, which the $20 word for that is isochoric. Constant pressure processes, that is called isobaric. Constant temperature is called isothermal. And then constant energy, I don't know why they don't call it isoenergy, but constant energy, they call that adiabatic. Now, just for our own sanity and simplicity, we're only going to consider this for sealed containers today. So later on, for those of you who are aerospace engineers, you'll have plenty of practice of problems where things are not sealed. So jet engines, car engines, for example, are not sealed. You have new gas coming in every time. But for us, we're just going to have some sort of sealed container. Think of a Tupperware container. And various things are going to be happening to the gas in that container. So we might add energy to it, things like that. All right. So the next thing is a video that I made a while ago that demonstrates a constant volume process. And it's going to be surprisingly simple. But I'll go ahead and let it play here. Maybe I can mute my microphone first. 5 kilopascals, and what I'm going to do is I'm going to put this in the hot bath. Again, this has a temperature probe in it. I'm also measuring the pressure over here. I'm going to put this in the hot bath, and we're going to see what pressure I get up to. So that was it. So all I did was I took an aluminum can that was sealed off with the aquarium tube, and that aquarium tube is going to a pressure sensor. And so I took the aluminum can, I put it into a bowl of hot water. None of the water got into inside of the can, but doing that made the air inside of this aluminum can heat up. And so that's all it was. So that's a constant volume process, because what it means is that the air inside of this aluminum can is not changing in volume. The only thing that's happening to it is changing in temperature. It's going from room temperature to whatever, hopefully the temperature that this hot water is set at. So what does that look like on this plot of a pressure volume plot? So think about that for a second while I go super fuzzy for some reason. All right. So on this plot, it's a constant volume plot, so that means we're not going to be doing anything special on the x-axis here, the volume axis. All we're going to be doing is increasing the pressure, so it's going to be a vertical line. And we're going to start at low pressure, right, because we're putting this thing into hot water. So we're starting at room temperature, relatively low pressure. We put that into the hot water, and that's going to make the pressure go up. And in that experiment, when I did it, I could look on the screen, because I have a pressure sensor, that can tell me how much higher the pressure goes, because the air inside of that aluminum can thing, the sealed off aluminum can, is now much hotter. Remember, ideal gas law, it goes as the density times the temperature. Well, the density is not changing, but the temperature is changing. And so this pressure is going to go up and up and up and up, like it does in the animation there. So that is a constant volume process. I think it's by far the simplest out of all the thermodynamic processes that we're going to talk about. We can figure out how much heat was transferred. So if we know how much the temperature changed, so let's say it goes from room temperature to whatever the temperature is in that beaker of hot water that I put it in, maybe we know what the change in temperature is, and we can figure out how much heat was transferred from the hot water to the air inside by taking that change in temperature, multiplying by the heat capacity. So this is the heat capacity. The sub V is not a multiply. The sub V means that it's heat capacity at constant volume, and there's a table to look that up later. And then this little n is just the number of moles. So specifically, this would be the number of moles of air that's inside of that aluminum can, would be the heat transfer. Now, something that I'll be emphasizing for each one of these processes is there work done? Is there work done by this object? Because eventually we're getting, towards the end of this thing, we're going to be talking about using multiple processes to make engines. And so when you're making an engine out of this, so that there's some sort of cycle of thermodynamic processes, you really care about which phases of that cycle that any kind of work happens, because that's the useful part of it, right? And so for each one of these thermodynamic processes, I have to say whether there's work done or not. Now, because nothing's moving, that means that the work done is zero. So all of this heat that the air inside the aluminum can receives, all that heat goes into increasing temperature. It doesn't go into moving anything around. And so, again, the work is zero here. And another way of saying that is that nothing useful can happen from just heating up hot air inside of a sealed container. All right. The next step, the next thing to talk about is isobaric processes, constant pressure processes. So this video shows a constant pressure process. And so we have a beaker here, we have a flame underneath, and it would be constant volume, except that this little plunger thing is allowed to rise and move up. And so what happens is if I get this thing hot enough, then that increases the pressure in here until it's larger than the pressure outside. Pressure differences makes things move, and so that is going to cause this little plunger to rise up. But when it rises up, the pressure goes down. And so effectively, at the end of the day, this pressure actually stays at the same value that it did at the beginning, but it rises and it rises and it rises. So again, the pressure differences makes things move. So as soon as the pressure is just slightly above the atmospheric pressure, it's going to rise, and it's going to go back down to atmospheric pressure, things like that. So that's right. So for our purposes, if you're really on the ball and you're really thinking about it, the main change in energy is that the change in gravitational potential energy of this plunger thing. If you think about it, you might also argue that the gas inside of it is also changing in its gravitational potential energy, because the center of the gas goes from being here to here. But the weight of this plunger is going to be much more than the weight of the gas, so we're going to ignore that there. So I think I said a lot of these things. Constant pressure. Let's see. So an analogy to this is inflating an air mattress. So an air mattress is all initially it's all floppy, and the pressure inside is the same as pressure outside, right? But it's not inflated, and so you put more air into it, and every time you put air into it, the pressure inside of that inflatable mattress gets a little bit larger than atmospheric pressure. That may expand just a little bit, But as soon as it expands, that pressure goes back down to atmospheric pressure, and then it stops. And so you add pressure, and then it expands. You add pressure, then it expands. The same kind of thing happens. So technically, that is a constant pressure process. But that's kind of another metaphor for what tends to happen. Now, what does this process look like on a plot like this? Again, we're heating this thing up and causing this plunger to rise. So in a second, there's this candle there. So what does it look like here? Well, the volume is changing now, right? So the volume is getting bigger. And so we know that it's not just going to be some straight line here like it was last time. The pressure, I mean, we're applying heat to the pressure. So that would make you think that the pressure goes up, but as soon as the plunger starts to rise, the pressure goes back down. So at the end of the day, you end up with this straight line for the pressure. So you start with this pressure, but because the thing is expanding, you keep with that pressure. And all the heat that's transferred to the gas ends up contributing to, that energy goes to increasing the height of that piston. So we can think about the work that's done by the gas to increase the height of the piston, right? So there's the weight of the plunger, right? So there's the force of gravity of the plunger down, right? But then there's the force of the gas up. And so if we're thinking about the force that this gas provides over some distance, that can tell us how much energy that it took to do this. So there's the force of the gas upwards times the change in height of the plunger. We can divide by, we can do something clever, which is to divide by the area of the plunger, and then multiply by the area of the plunger. And so the interesting thing is that when we divide the force by the area of the plunger, we just get the pressure of the gas on the plunger. So we end up with the pressure of the gas, and then the area times the change in height, so the cross-sectional area here times the change in height represents the change in volume. And so what matters is the pressure of the gas on this plunger times the change in volume that this thing rises. I mean, I could have left it as the area times the change in height, but it's slightly more general to write it as the change in volume there. So there you go. So that's the work done by the gas. Now, an interesting discussion is how much work does it take to compress a spring? And you guys kind of already know the answer to this because we've talked about it in the past. So this is a slide from earlier in the course where you're going to compress some spring over some distance, and initially it's really easy to compress the spring because the restoring force is basically zero initially, but then as you get going, the restoring force gets larger and larger and larger. What matters is the average force over that distance, and so you take these two forces together and just divide by 2 to take the average, and then you multiply by what distance that you compress the spring. Again, initially the force, the restoring force is basically zero. And then towards the end, the restoring force is k times that maximum distance that you're trying to shove it, and so you end up with the work that it took to compress the spring is this, which is also the work that the spring is storing, if you want to think about it that way. An interesting way of thinking about this result is in more of a graphical sense. So, for example, if I think about the force that the spring, the restoring force that the spring provides, the more I compress this spring, the more force it requires, and to the point where I get all the way to here, which is sort of the maximum compression that I'm going to do, the delta x. And what's interesting is that if you think about the area under the curve, well, the area under the curve here, so the area is 1/2 base times height, right? So the base here is delta x, the height here is f, and so 1/2 f delta x, well, remember f is k delta x, and so 1/2 f delta x is just the area, it's just the area of this triangle. That's where the 1/2 ultimately comes from. And so the moral of the story is that the area under the curve can tell you how much work it takes to do one thing or another. So I'm not really going to talk about springs for the rest of this lecture, really, but I just want to point out that the area under the curve is a good way to think about how much work it takes to compress a spring, or alternatively, how much energy it's storing. So when I take the same approach with these thermodynamic processes, it turns out that the area under the curve of the pressure volume plot can tell me how much work is done. So if I have a constant pressure process going from here to here, so it's constant pressure, so that's not so interesting, but the volume is definitely changing. Well, the work that's done, if I take the area under the curve, it's just the pressure of this gas, like the constant pressure of this gas here, times the change in volume here. That gives me the work that's done. And so the same approach with the spring works here, which gives me the work done is the area under the curve. So I've shown you 2 or 3 different ways to arrive at that conclusion. Now in terms of whether this is useful or not, it actually sort of is. Like, you could, in principle, you could have this as a kind of an elevator. I don't know anyone that would want to do it this way, but you know, Charlie and the Chocolate Factory or something, if you wanted to have some kind of steam-powered elevator that you apply a flame to, and the steam expands to bring this elevator up to the top floor, well, that is work done. That is useful work done, especially if it's a freight elevator. So there is useful work done here, and we'll think about that a little bit later when we think about engines. And when we think about the useful work, we don't think about the various sources of heat transfer to heating up the glass or anything like that. We're only thinking about the heat that goes from the candle into the air there. All right, so I think that covers it for constant pressure processes. The next process is constant temperature. So let me talk about that. I think I need to mute my microphone again here so you can see the video. All right, so I'm going to collect, and then, so now 99 kilopascals, 26 degrees centigrade. Stick this into here, so now the pressure is going up. I'm up to 106 kilopascals. And now what I'm going to do is I'm going to compress this down, see how I can get. And I went up to 119 kilopascals. Okay, so in a way that was two processes, one after another. So that was, there's an aluminum can that's sealed off, and that is put into a hot water beaker. And so first there's a constant volume process. So not all the constant temperature processes have to start with constant volume process, but I did that first in that demo. I wanted the air inside of it to come up to some temperature. So what I did first was constant volume, isochoric. And then what I did is that if you look very closely at that video, and maybe I can just play the video back without the sound now. So I'm going to collect, and then now 99 kilopascals. So in that video, you'll notice that there's this aquarium tube that's connected to this thing, and then this thing in turn is connected to a pressure sensor, so I can figure out what the pressure is inside of it. But the important thing is that I'm going to compress this thing down. So it's all sealed off, but I'm basically making the volume smaller here because I am compressing this piston down. So everything's up to a temperature, and the temperature is not changing. What is changing is the volume. So it's not a constant volume process for sure. It's not a constant pressure process because the pressure is going to go up because I just decreased the volume, right? Because that increases the density. So ideal gas law goes as density times temperature. So if I decrease the volume, I'm going to increase the density because there's not as much space for all those air particles to be. But what is constant in this process is the temperature. So it's going to come up to this temperature, it's going to stay at that temperature, And if you could see my screen, I'm looking at I have a temperature sensor here, and I've got an air pressure sensor over here. If you could see my screen on this demo, it would show you that the temperature is very constant. So in a pressure volume plot, there is a volume pressure plot. So I've been mostly giving you pressure on the y-axis and volume on the x-axis. This is a nice plot that shows you, except that's the opposite. And basically what's happening is that the temperature is constant. You see the temperature is at 300 degrees Kelvin. And we're putting more and more weight on this thing. So I was physically pushing down on it. Here they're putting little masses on this thing to increase the pressure. And so the pressure is going up and the volume is going down. So again, this is a constant temperature process. Now on the next slide, I can take a look at that and think about, well, what does this look like on a pressure volume plot? Not a volume pressure plot, but a pressure volume plot. So now we can think about, what does this process look like on this plot? So this is a pressure volume plot, not a volume pressure plot. So you can kind of flip those axes, and you'll find that, give you a second to think about it. You'll find that as the volume becomes smaller, the pressure goes up, right? And so you're going to find something that looks either like this, so the pressure is going up and going down, or the opposite, in which the volume is being compressed and the pressure goes up. So one of those two things is happening. And we know that the ideal gas law is true. And in this case, because we have a sealed container, the number of particles is constant. So you remember in that previous lecture I gave you like 3 or 4 different versions of the ideal gas law? Well, depending on the situation, one of those versions is easier to understand than the other ones, are more helpful. And so in this version, because it's all a sealed container, the number of particles is the same, but the volume that those particles exist in is changing because we're compressing this thing down. And so if you figure that this is equal to a constant, right, because the temperature is constant, then this gives you a curve that goes as 1 over v. So if you wanted to calculate this, plot this on your calculator, you would do y equals 1 over x to get this kind of a curve. So here's a question: Is there a heat transfer in this process? Again, let's figure that it's going from large volume down to small volume and to high pressure. Is there heat transfer? In other words, is there heat transfer from sort of the ambient environment into the air that's inside of this thing? And the answer to that question is yes. So it matters what the temperature outside of this thing is, for example. And is there work done? Well, the question of whether there's work done, this question is often quickly answered by the question, has anything moved? And indeed, there are things that are moving here. And so yes, there is work done. So we'll talk more about that in just a second. So let's say that we are going to compress this thing. So we're starting from some pressure here, and we're going to go up, 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 and up, and up to some higher pressure so that the volume gets smaller. It's harder and harder to compress. So let's try to calculate how much work it takes to compress this thing starting from here all the way up to there. Now remember, the work is the force times the distance. And so we're going to use the ideal gas law to figure out what the pressure of the gas is. The pressure of the gas times the area gives us the force, and then we're going to think about over what distance that we're compressing this thing. So this version of the ideal gas law is the one that's most helpful for us. And if you think about it, we have some container, right, that has some cross-sectional area, and we are changing the placement of that plunger there. And so you can just say, well, the volume there is A times X, where X is the position of that plunger. And so that's going to be the pressure. You could say the work is the area under the curve. It's also true that the work is the force times the distance. And so if I take the pressure times the area, that gives us the force, right? And then, so I can sub this into here. Now, of course, you notice that the area here is going to cancel with the area there. So you notice that there's no factor of A in here anymore. And what we're going to do is we're going to break up this sequence into tiny little pieces. And so we're going to go, so as we compress this thing, we're going to go shove, 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 shove until it gets all the way to that smallest volume, right? And so this sum thing is just a scary symbol that says each time we're going to compress this thing, and as the pressure gets higher, it's going to be harder to compress, but we're still going to compress it by some amount each time. And so if you count up all those things, and if you do that with tiny enough shoves, you end up with basically the integral of dx over x. Now this n, k, b, t, these are all constant. Remember, this is a constant temperature process, so these can all go out front, and I could have written it like that here if I wanted to. But you're going to end up with some sort of integral of dx over x, which, if you know from your calculus classes, is natural log. So you end up with this sort of a thing. So you end up with, again, so this is a constant that goes out front. You end up with the natural log of sort of the final position of the plunger divided by the initial position of the plunger. And we can make this a little bit more general. So this is specifically for some container that we have where the container's not getting any wider or smaller, which is probably true for most containers. In principle, if somehow this thing could shrink in all the directions, there's got to be some sort of application where this could happen. Well, then you can just say that it's the change in volume. And the reason you can do that is because, if you multiply A on the top and A on the bottom, this very quickly becomes a change in volume. So anyway, so this is the most general formula for the work done. So again, it takes a certain amount of work to compress this thing from its initial volume to its final volume. That work is given by this. And if it was going the opposite way, if it was expanding, well, then that would be useful work done by the system. If we're compressing it, then that's the work that we do to the system to get it to compress. So there is work done in this case. So you might wonder what happens if you compress the piston really, really fast. So let's say we have this plunger on this gas, and instead of like slowly pushing down on it, instead we tried to compress it as fast as we possibly could. What would happen in that case? What would happen to the temperature? What would happen to the pressure, etc.? It turns out that actually, if you do it fast enough and you compress it, it actually does cause the temperature to increase. So one of the interesting things about the isothermal processes, which we've been talking about, is that the temperature inside of the gas there stays constant even as you are compressing it or expanding it. And the reason that happens is because there can be heat exchange. And so if you're inside of a hot thing you compress it down, well, the air inside might get hotter, but then it can exchange energy with the outside and cool down to whatever the ambient temperature is. So for isothermal processes, this temperature does increase if you compress it. Sorry. Let me start over again. Now here's kind of a fun question, which is what happens if you compress the piston really, really fast? So you saw in that video I took that little plunger thing and I sort of gently pushed it down. But what if I pushed it down as quickly as I possibly could? And the question is, what happens to the pressure? What happens to the temperature? And is it really true that the temperature would stay constant, even if I compress that thing rapidly or allow it to expand rapidly? And the answer is that the temperature really would change. So especially if you compress it, the temperature would increase if you compress it fast enough. And so it would not be a isothermal process if you did it fast enough. So all of the isothermal stuff I've been talking about is for cases in which that compression is happening relatively slowly, which relatively slowly can still be pretty quick. But at some point, if you do it fast enough, you actually would get a temperature increase, and I'll tell you why in the next slide. So the reason that it matters how quickly you do it is because if things happen fast enough, then there simply isn't enough time for the gas inside of the piston to exchange energy with the outside. So if you are compressing it, for example, so let's say you're in room temperature and you compress this gas very quickly, then what can happen is that as you compress it, that increases the temperature and it increases the pressure. But if you're doing it relatively slowly, well then what can happen is that there's heat exchange between that glass jar and, say, the room temperature. And so instead of having gas inside of this thing that is warmer than room temperature, it actually pretty much stays at room temperature even as you compress the thing down. And in fact, if you could have seen my screen when I did that demo in the video, you would see that indeed the temperature stays very constant even as I'm compressing the thing. However, if you do it fast enough, if you compress the thing down fast enough, then there isn't time to do this heat exchange. So this is what's called adiabatic compression now. There's just simply not enough time to do the heat exchange, and so at the end of the day, you're going to find that both the temperature has increased and the pressure increased. The pressure has to increase because you're decreasing the volume. That's not the question. The question is whether the temperature also increases. And if you go fast enough, it turns out that just there's just simply not enough time for it to stay at the ambient temperature. So what does this look like on our pressure volume plot? Well, if we're going to compress it, it's going to go from high volume to low volume, right? The pressure is going to go up, but the question is by how much? So these black lines, not the dashed one, I'll talk about the dashed one in just a second, but these black lines are what's called PV curves. And it mentions the temperatures here. And so this is, so everything that is of temperature T1, if it's an isothermal process, is going to stay on this line. Sorry, it's going to stay on this line as you compress. Everything that starts at this temperature and stays at this temperature is going to start up here. It's going to stay on this line even as you compress the thing. But if you compress it so fast that both the pressure goes up and the temperature goes up, well, then you're not going to stay on this curve, on this PV curve. Instead, you're gonna rise up to this other curve, and so you're gonna end up finding that the on the pressure volume plot, you're gonna end up with something that's quite a bit steeper than it would be if it was just an isothermal thing. Sometimes these are called isotherms, these PV curves. But anyway, this is what's called adiabatic compression. And this line, which again is for the adiabatic case, is sometimes called an adiabat. And again, it's assuming constant energy because there's not enough time for the heat to exchange. It turns out that the opposite process is possible. So not just compressing things, but also expanding it. So instead of me pushing down on the thing and very quickly and trying to increase the temperature, it turns out that if it expands fast enough, that the opposite can happen and the gas can cool down. So this the most dramatic demonstration of this, I would say, is, say for example, in a refrigerator. So I have a worksheet that is optional, but it's good to review for the exam. that talks about how when you have a liquid that's evaporating, what that means is that it's expanding very rapidly, and that expansion causes it to cool down. And so basically everything that cools things down, your refrigerators, works from adiabatic expansion. And the thing to say about adiabatic expansion, out of all the thermodynamic processes that I described today, this is the only one that actually leads to any kind of cooling. So in the next slide, I have a video of me, and what I'm doing is so instead of compressing that piston down, so I have air in a sealed container. Instead of using aluminum, I'm using a glass beaker, which is a long story. But I have a temperature sensor inside of it. And I have another little plunger thing. It's actually a syringe, but it's overall pretty similar. And what I'm going to do is I'm going to pull up on that syringe to make the volume increase. And I'm going to look on my screen to see if the temperature drops. And it turns out that it will drop by just a little bit. So let me go ahead and turn the sound on for that so you can hear it. Recording? Great. Okay, so I have this beaker here that's sealed off, and I have this syringe that I can pull up on to make the pressure inside of this thing drop dramatically. Now if you look closely at this thing, there's actually water in there, which is kind of a clever thing to do, and what I'm trying to do is water is incompressible, so I can compress and expand the air as much as I want. The water's not going to do anything. But what that does is that means that my change in volume, instead of changing the volume by 30% or something like that, by making the syringe go up, I can change the volume by like a factor of 2. And so, as I say in the lecture, if I do this fast enough, I should be able to make the temperature drop through adiabatic expansion. So all the other processes, like isothermal, those are constant temperature processes, or maybe the temperature is going up, some things like that. This is really the only process where the temperature drops. So let's see if this happens, and I'm going to go ahead and collect the data here. Let me see if I can put the cursor over the green thing. I can't see it. All right, there we go. All right, so I'm collecting my data. It's at atmospheric pressure, 100 kilopascals, and I'm going to go ahead and pull this down. And you're going to see the pressure just drop dramatically, and you want to look carefully at the temperature, see if the temperature drops too. Ready? I'm going to pull the syringe up. The temperature is going to drop. There it goes. Drops all the way down to something like 67 kilopascals, and you can see pretty clearly that the temperature dropped by maybe 0.2 of a centigrade, something like that. And now over time, the temperature is going to climb back up again, because this only works when it happens rapidly. So over time, despite the fact that the air is cooler inside of this thing, the outside of the container can exchange energy with the inside of the container through the walls of the thing, and it'll sort of climb back up to room temperature. And so, if I had done this very slowly, it would have just stayed room temperature, but because I did it rapidly, it actually drops. It drops and sort of comes back up again. And I can let go of this thing. I can let go of the syringe. So the syringe is kind of coming back down, and the pressure inside is going to go back up to room temperature. So you can see the pressure kind of going all the way back up there. Okay. So there you go. So I showed that the temperature really does drop. And the importance of this thing is that if I was going to do adiabatic compression and show that the temperature increases when I do this, when I compress it instead of expand it, one can imagine that, well, really the temperature increase was from, say, the friction on sort of the rubber tube here against the side, and you might accuse me that the temperature goes up because of that instead of because of this adiabatic process. But here, because I'm doing an expansion, there's still that friction between the rubber and the side, and so you might expect the temperature actually to go up because I'm expanding it, but in fact it drops. So hope you enjoyed that video there. So adiabatic expansion on this plot is going to start from up here, right? Because I'm starting at some temperature. But then very rapidly I'm going to go down to some lower temperature because the volume is expanding very quickly. And so this curve is defined by this formula. So this is the pressure, the volume, and then this symbol here is called gamma. It's a Greek symbol, which I'll talk about in just a second. Now again, if this is equal to a constant, and by the way, if you remember with the isotherms, it's P times V equals a constant. Now it's P times V to some power equal to a constant, so it's something different than isotherms or isothermal case. I'll talk about that constant in just a second. This is another way of writing the equation, right? Because if this multiplies to a constant, no matter what the pressure and the volume is along that curve, well, that means that the initial pressure times the initial volume to that power equals the final pressure times the final volume, again to that power. Now, what is the constant that we're talking about? This to the power of thing. This is called gamma, and every gas has what's called a gamma constant. And so, for example, the gas in this room and in any room is a gamma constant of 1.4. So those of you who are heading to be engineers or anything, we think a lot about air in our lines of work. The gamma constant for air is 1.4. So if you're going to do adiabatic expansion in air, 1.4 is the exponent to put in there. The book refers to gamma as the ratio of molar specific heats. Because it has to do with, it so happens to have something to do with how much things raise in temperature based on their energy and based on whether you're doing things at constant volume or constant pressure. So that's how the book defines this as the ratio of molar specific heats. I prefer to call it the resistance to compression for some reasons that I'll talk about in just a second. But this is the table from the book. So gamma equals gamma here. And what you notice is that for all of the so-called monatomic gases, so helium, for example, helium in your helium balloon is not in a molecular form. It's just helium atoms bouncing around. They're not, there's no molecular or any kind of chemical bonds between those helium atoms as they're bouncing around. And it's the same thing for argon and neon and krypton. These are all noble gases, and so they just bounce around alone, basically. But hydrogen would not do that. Hydrogen, you cannot just have bare hydrogen bouncing around inside of a balloon. The hydrogen will bond with itself to make H2 molecules. Same thing with nitrogen and oxygen and all these other things. So these are what's called diatomic gases because two atoms are bonded together somehow. And these kinds of gases, they don't all have exactly 7/5. So 7/5 would be exactly 1.4, right? Because that would be 1 and 2/5, and 2/5 would be 0.4, right? They don't all have exactly 1.4, and this one is 1.41, this is 1.35, but it's overall pretty close to 7/5 for some reasons that the book explains. And then these are polyatomic gases, so instead of having two atoms that are bonded together in a molecule, these are 3 or more, so methane here is 5 atoms that are bonded together. And these have yet a different gamma constant. And the difference has to do with the ability for these things to store energy, which I'll talk about in a second. I like to call gamma by the way, air is made up of diatomic nitrogen and oxygen, and so the reason I said earlier that air has a gamma constant of 1.4 is because all the stuff that makes up air has gamma constant of 1.4. So that's where that comes from. I call gamma resistance to compression, which is something that Kip Thorne came up with. So Kip Thorne here is the brains behind the movie Interstellar, which is not my favorite movie. He also won the Nobel Prize for gravity waves in 2017, and he was very good friends with Stephen Hawking. Anyway, he liked to call gamma the resistance to compression. And the reason that he coined this phrase in his book, Black Holes and Time Warps. And he's always self-promoting, which is kind of annoying to me. He always wants you to buy his book. But, you know, if you're at Caltech and you've done everything else, you may as well try to get people to buy your book. And the reason he likes this, calling it resistance to compression, is because it literally is harder to compress gases that have higher gamma constants. So, for example, if you take gamma 5/3 compared to 7/5 compared to 9/7, well, the largest one is 5/3 because 5/3 is 1.67 or something like that. Whereas diatomic gases, this is closer to 1.4, and then this is less than that. So the largest gamma constant is the monatomic gas. And if you think about what this PV to the gamma equals a constant means, is that if you take a meter cubed box and you compress it by some amount, well then according to PV gamma equals a constant, the pressure is going to go up according to that equation, and the pressure goes up the most if you're dealing with an atomic gas because this gamma constant is the largest. So the easiest gas to compress would be the polyatomic gas, and the hardest gas to compress would be the monatomic gases like helium and things like that. And the reason this happens is basically that the reason this happens is basically that the monatomic gases get hotter as you compress them. Again, you're compressing it rapidly, but they get hotter as you compress them because the only way it can store that energy is in the motions of the particles zipping around that container. And so if you rapidly compress it, those particles are going to be that energy is going to go into the average speeds of those particles. The average speeds of those particles are going to cause it to hit the walls of the container more quickly and harder because it's moving faster, and so that is ultimately going to cause the pressure to go up. Whereas for the polyatomic gases, if you rapidly compress that container, some of that energy goes into the average speeds of the particles, but other energy goes into how much the particle is spinning and how much the particle is vibrating. So molecules like to wiggle, by the way, which is how your microwave works. So when you turn on your microwave, what it's doing is that it turns out that water molecules, so you've got the oxygen and you've got the protons. So here's the oxygen and here's the protons over here. Water molecules like to wiggle. And so, and they wiggle especially at 2.4 gigahertz. And so if you irradiate them with 2.4 gigahertz radio waves at high power, they will start to wiggle at that speed. And as I said earlier in the lecture, vibrations are related to temperature. And so the more they vibrate, the higher temperature they get, until eventually your food is at the temperature that you want it to be. And so what's happening here is that because the polyatomic gases, like H2O, methane, all that stuff, because they can both store energy in their spin and in their vibrations. Well, the thing about that is that if a molecule is spinning rapidly and it hits a wall, it doesn't have a significantly different collision than if it was just moving rapidly and hit the wall, if that makes any sense. Or if it's vibrating and it hits the wall doesn't care. The wall only cares about how quickly it's coming in and going out. The wall only cares about, say, the average speeds, basically. And so as you compress these things, the fact that you can store energy in that vibration or the spinning of the diatomic gases or the polyatomic gases means that it's easier to compress those because more of that energy is going into a form that's not really affecting the way that it collides with the walls of the container. Anyway, so that's the big explanation of why that all happens. Another thing to say is that the ideal gas law still applies here. So just because it's adiabatic compression and just because it's PV to the gamma equals a constant, that doesn't actually mean that the ideal gas law does not apply. The ideal gas law totally applies. It's just that both the density is going up and the temperature is going up. So I said earlier that it is remarkable to me of just the wide range of situations that the ideal gas law is true. And I'm telling you, in this course, the ideal gas law is true for every question that I can ask. Every question that could possibly come up, the ideal gas law is completely valid. It doesn't break down except for very unusual circumstances that I promise Scouts. Is it this or that one for the Scouts honor? That I would not bring into this course. Yeah, like another way of saying that the monatomic gas is hotter than the other two. So this is the adiabat, as I was saying, that this is, there is work done here, right? Because things are moving. And if this thing was expanding, then it could potentially do work, right? Because if you imagine this is very hot and you let it expand, that could be a very useful work for a factory or an elevator or something like that. And so you might want to find the area under the curve. I'm going to spare you of that calculation because it gets into a little bit of calculus, which is sort of beyond the scope of this course. So I don't need you guys to be familiar with that, but I do need you guys to be familiar with the principles of what's going on here. All right. As I was saying, the ideal gas law is still applies here, and in the worksheet you'll find that if you apply the ideal gas law to this equation, you'll find that the relationship between the temperatures here are like this. And so you can convert this to that using the ideal gas law, which maybe, sometimes this is useful because I might want to ask you what's the final temperature of some situation. Okay. So your worksheet is involves compressing 3 cylinders, and you'll notice that I've chosen 3 different gases here. This one, I hope you can see, is a monatomic gas. This one is a diatomic gas, 2 hydrogens bonded together, and this is a polyatomic gas, which is three atoms bonded together. And you can compress all those. We're going to compress them rapidly by a factor of 2, and we're going to see what's the final pressure and temperature in each case. So that's the group work that's for this lecture. Before I go, I want to give you a few example questions to think about that or just maybe prep for the exam or whatever you want. You don't really have to do them, but I want to walk through them here because this is the kind of thing I might ask on the final. So let's say if the volume of a sealed container of glass is decreased, keeping the total amount of gas fixed, then the temperature will increase, decrease, stay the same, or we simply don't have enough information to answer. What do you think? So I would say the best answer is that there's not enough information, because if you decrease the volume rapidly enough, well, then the temperature would go up. But if you do it slowly enough, the temperature would stay the same. And so there's just not quite enough information here to figure out if the compression is isothermal or adiabatic. Here's another question. So two identical cylinders have the same amount of gas at the same pressure, but cylinder A has twice as much gas as cylinder B. So what is true about the temperature of cylinder A and cylinder B? So let's think about this one. So as I said, the ideal gas law is true in every question in this course. And so they have the same kind of gas in cylinder A and cylinder B. But cylinder A has twice as much gas as cylinder B. So the volumes are the same. But because there's twice as much gas in cylinder A, that means it's going to be twice as dense as cylinder B, but it tells us it's the same pressure. So if cylinder A has twice as dense as cylinder B, but they have the same pressure, then the only way that that can happen is if cylinder B has significantly higher temperature than cylinder A. So in other words, that cylinder A has all this gas in it that is bouncing off of the surface of the container, causing a nice high pressure. Cylinder B has much less gas, but it's still producing the same amount of pressure. The only way that that's possible is if the temperature in cylinder B is larger than the temperature in cylinder A. So this is the kind of question I might ask you guys on the final, let's say. All right, here's another one. Two cylinders contain the same type of gas at the same temperature, but cylinder A has twice the volume as cylinder B, and it contains half as many molecules as cylinder B, which is, maybe it's over here. So what is true of the pressure inside of cylinder A compared to the pressure inside of cylinder B? So let's see. So if cylinder A has half as many molecules as cylinder B, that means that if they were the same volume, the density would be half as much. And if they're the same temperature, then that would mean that the pressure is half as much in cylinder A as in cylinder B if they were the same volume. Right? But they're not the same volume. Cylinder A is twice the volume as cylinder B. And so cylinder A has half as many molecules, which would lead to half as much pressure, but then it's twice the volume, which would cut the pressure in half again. So I would say that cylinder A has 1/4 of the pressure of cylinder B. All right, here we go. Question 4. A cylinder of gas has a frictionless but tightly sealed piston of mass m. And what we're going to do is we're going to increase the gas temperature from 27 degrees centigrade to 127 degrees centigrade. What is the ratio of the final volume to the initial volume? So let's see here. I have to think about this one myself. So this is going to be a isobaric process, because as we heat the gas up, the piston can climb higher and higher because it's changing in volume, right? And so we know that the pressure is staying the same inside of this thing. It's just that the temperature is going up and the density is going down. And so what that means is that we can use the ideal gas law to figure out what the change in volume is. So the way we would use it would be to say that PV equals NKT for both cases. And then the number of particles inside of this thing is the same. The pressure is the same. And so the ratio of the two volumes should be the ratio of the temperatures. The thing is, though, that the ratio of the temperatures, they give it to us in centigrade, but when we do PV equals NKT, we're really thinking about temperature in Kelvin. And so for this case, we're going from 27 degrees centigrade, that's 300 degrees Kelvin, to 127 degrees centigrade, that's 400 degrees Kelvin. And so the ratio of the temperatures is 400 Kelvin over 300 Kelvin, and so the ratio of the final volume to the initial volume should be 4/3, which is 1.33. So maybe I should just write that out. But anyway, so those are some example questions that I hope you'd be able to do by the time we get to the final. But send me an email if you have any questions, and I hope this was a helpful lecture. Thanks.